Well, this is it, the last of the videos for our organic unit. So it's been a pretty big unit. So now we're just going to look at benzene as a special case. So we've mentioned benzene, we've drawn benzene a few times. Now we're going to talk about how it's different in terms of its reactivity and the specific things we need to know about its structure. So benzene has a particular stability in that it doesn't react very much and has its own particular set of chemical properties. This is because it doesn't behave like other alkenes. There's no isomers of benzene, and it's very stable because of these delocalized electron clouds that we get above and below the ring. So essentially, we should be hopefully familiar with the idea of benzene being this six-membered ring structure where we have alternating double bonds between each carbon. And we know this is the Kekulé structure, and we've talked about this a little bit before, but Kekulé, they didn't know the structure of benzene. No one could figure it out. It had this molecular formula that they knew, but they couldn't figure out how to put the molecule together following all the bonding rules until they realized that the carbon chain could actually come around and attach to the carbon, forming a ring system, much like Kekulé described it, like a snake biting its own tail. And what this does is provide what we call the aromatic ring system. Okay, and this aromatic ring system is this alternating series of double bonds, because we can say that the double bonds are in constant movement between this position or the position where they all change by one, but they're always alternating double, single around the ring. So usually we show benzene without any of the hydrogens attached, but it is important to remember that they're still there, and we actually have, like on this one here, 6 carbons and 6 hydrogens, so it has the formula C6H6. Okay, so the interesting thing about benzene in terms of it is all the carbons are bonded in exactly the same way. So they're all bonded to form a cyclic structure with an angle of 120 degrees. So when we look at it, this angle here and here, so this is 120, so we've got that trigonal planar kind of arrangement around the carbons. So what this does is we have one leftover electron per carbon, much like what we saw in graphite, and they don't pair up. They form these alternating double bonds around the ring. Okay, this delocalization provides a symmetrical cloud where the electrons are all evenly distributed over this large ring structure. So we can draw it in a couple of different ways. This is our 120 degrees around here, and then we have these p orbitals. Okay, so you may remember that our s orbital is round, like a sphere. So this is an s orbital, and then p orbitals have this bilobed shape. And then what we get is this sideways, you'll notice here they're overlapping a little bit here. And this sideways overlap forms what we call a pi bond, which we'll talk about more later on in higher level. But this pi bond system essentially means that the electrons can travel around in this donut-like cloud above and below the ring. Okay, so which is what makes it so stable. So when we draw benzene, we show these double bonds, but more often we show this one, which hopefully you remember. Whoops, I'm going to run out of battery. Is a resonance hybrid, and this resonance hybrid tells us that it's not truly a single bond or a double bond. It's actually a mixture between the two. So the resonance hybrid is could be this one, but also is just as likely to be this form. Okay, so the resonance between the two. You have to remember to draw in the ring. We can't just draw it as a hexagon, because then we're drawing cyclohexane, which has no double bonds and is an alkane. So because of its particular stability, even though benzene contains double bonds and is an alkene by definition, it doesn't undergo addition reactions like other alkenes, okay? Because of this stability of the conjugated pi system, or the conjugated double bonds, it's so stable it's not going to undergo addition reactions. It can, however, undergo substitution reactions like alkenes. Okay, and in this case we're going to swap out one of the hydrogens for something else. And in this case we talked about nucleophilic substitution. Now we're talking about, with benzene, it's electrophilic substitution. So where a nucleophile was an electron-rich substance that contained a lone pair of electrons or a negative charge, such as OH-. You'll remember this was a nucleophile. Okay, which now we're talking about electrophile. So this is electron-loving. So they're electron-deficient, partially positive or positive charge, so that they're attracted to things that are electron-rich. Okay, which would be the ring in benzene. Okay, so an electrophile by definition is an electron-deficient substance that forms a bond by accepting an electron pair. Electrophiles are positive ions or have a partial positive charge. And the two that we're going to look at are the nitration of benzene, adding a nitro group to it, and then the chlorination, which is adding a chlorine to it. So for the nitration of benzene, this is the reaction you need to know. It's an electrophilic substitution reaction, and you have to know the conditions and the resultant products. So we take benzene, we add nitric acid in a mixture with concentrated sulfuric acid, and we heat it gently. When we do that, we will form nitrobenzene, okay, and water as a byproduct. So you need to know that we take benzene, we need to know the conditions of the nitric acid and concentrated sulfuric acid with heat, and these products as well. So it's another one to add onto your reaction schemes. The other one we need to know is the chlorination. Okay, so reacting benzene with halogens, we start with benzene, we add in chlorine gas, we add aluminium chloride in dry ether, so we have to know the solvent conditions here. We don't want any water present in this, is essentially what this is saying. So we want dry ether and then aluminium chloride, and we will get chlorobenzene and hydrochloric acid as a byproduct. Okay, so we can also form bromobenzene. In this case, however, we will form HBr rather than HCl, and we will use an aluminium bromide catalyst rather than an aluminium chloride catalyst. So there we go. That's pretty much all we have to know about benzene. There is a summary for it in your textbook. You should pay attention to the bond lengths, remembering that because it has resonance, this will it won't have a true double bond character or a true single bond character. It will be somewhere in a 1.5 bond order, so somewhere in between the two. The bond length would be between the two, and we can see that from experimental data from X-ray crystallography, that the bond lengths are not as short as they would be if they were double, not as long as they would be if they were single. So we can see experimentally the proof for that. We can also see this through the bond enthalpy, that the theoretical value would be negative 362 kilojoules per mole. The experimental value is negative 210 kilojoules per mole. So what we're finding is that it's more stable. Okay, so it's more stable. We have a higher stabilization because of the resonance. The reactivity, because of the presence of the double bond, we would expect it to undergo addition reactions. However, they're not favored due to the high stability, so it undergoes substitution reaction, and that there is no isomers. If we add bromine across this and do a double addition reaction, here there's no isomers because all the carbons are exactly the same. Okay, so they're all alternating between the double bonds, so we get no isomers. So that's it. Hopefully you can make some good notes on this. And the other thing that I will just point out is that when we have benzene as a functional group, we call it an arene or a phenyl group. Okay, so this is when it is a functional group on a carbon chain, attached to a carbon chain. Okay, so when it's not just on its own, we refer to it as an arene functionality or a phenyl group. Okay, so that's it, the last of the organic chemistry. Now it's just a matter of revising and getting ready for your test. Good luck.